Thank you, Danielle, and good afternoon to everyone. Today we'll talk about, in a very high-level sense, seismic data processing. Tuesday past, we talked about acquisition, and so today we'll follow up with processing. The eye candy on the first slide, I have a common midpoint gather, a velocity semblance diagram, and then this common midpoint gather has been flattened using the velocities. And I'll talk about these different steps and explain the terminology as we go along. I've included this, the terms of use. It's also on the IRIS webpage where the lectures and exercises are located. These materials are intended for use in training students at the university and grad level. They are not intended to be used by people who are already working in the industry through self-study or in-house courses or through contractors. So I'll talk a little bit about processing. We'll talk about the basics of a stacked seismic section. Then I'll talk about some of the pre-stack processing steps, and then we'll talk about seismic migration. So the objective in doing seismic data processing is to obtain an accurate, interpretable subsurface image. So seismic data acquisition and processing, they work hand in hand, and the ultimate goal is to get good interpretable images. We would like the process seismic to represent the true Earth response. In practice, the even best process seismic data is only an approximation of what that real Earth response or structure is. The image I show here on the right is a reasonably well processed section from a seismic 3D volume. We have a fault that's here, and there's a major unconformity that runs across the section through here. And so the bands of blues and whites and reds and oranges is telling me something about how the rocks are layered in this part of the world. So with processing, we start with our field records, the raw data. This is a marine data set, and you can see the hyperbolic reflections. Those are the reflected energy. That forms our input to the processing stage. We do some processing in the field, either on ships or on the land processing crews, but most of the processing is done in big processing centers. And what we hope to get out is images of the subsurface from which we can deduce the geology and hopefully the fluid content of potential reservoirs. So the challenge, we want to estimate and remove the effects that are not geological, and those things I tend to call artifacts, things that are not real from a geological, geophysical point of view. And we would like to remove the impact of those artifacts on our amplitude and the phase of our primary reflectors. If we understand how waves propagate, and the equations have been worked out fairly thoroughly, we can develop and then apply corrections to get a more accurate image of the subsurface. So elements of good processing, one element is the accuracy of the geometries that it's showing. Reflection times are free from distortions and show us what the true trap definition is. Another key element is to try to compact the wavelets. We want to get the correct reflection amplitudes that are associated with the impedance contrast. And we want the pulse shapes to be as short in time duration as possible and as stable as possible. And if we have that, we can then make predictions about lithology and fluids. And we want to also reduce noise. The signal that we want is the geological information, and anything that isn't part of that geological information is either noise or artifacts. So on the right upper, this is pretty good processing. This is a section from South Texas, I believe. It was reprocessed, and you can see that the image on the top has sharpened up quite a bit at the base. This particular fault plane is, you can see it, but it's a little uncertain exactly where it lies. It sharpens up quite a bit here. The reflection bands, the blacks and the reds, are sharper, shorter time duration in the lower image. They're a little thicker in the upper image. Oops, I'm sorry. So I'll talk about a generic processing flow. We do our processing in several steps. We do some signal processing originally. We try to control and shape the wavelet. We try to preserve the relationship between seismic amplitude and the reflection coefficients that generated the reflections. And we try to improve the signal-to-noise ratio, SNR, signal-noise ratio. Then we do some imaging. We're trying to focus the subsurface image. We're trying to correctly position the reflectors to be in the right XY depth space as they are in the Earth. Most of that imaging we do through the seismic step of migration. And then we may do some more signal processing after we do the migration, and some of that can be done prior to the stack, some can be done after the stack. So the two basic types of seismic processing focuses on where exactly in the stream we do seismic migration. The quickest and less expensive and maybe the classic method is to do migration after we stack the data. And so here we have some front-end geometry corrections, amplitude and phase control, noise mitigation, and then we stack the data. That's where we sum source-receiver pairs that come from a single subsurface reflection point. We do velocity analysis and we do the seismic migration. And so that is after the stack. And then we have some post-migration processing that we can do to try to further enhance the image. The other way to do things is to do the stacking before we do seismic migration. So the same type of signal analysis, we do our velocity analysis and we do migration, and that is before stack, and then we'll stack the data in this step and maybe do some post-stack processing. Pre-stack migration is very much more expensive and takes more time, takes more people, takes more compute power than post-stack. So I've talked about stack. Let's talk about what a stack section is, and then we can talk a little bit more about some of the steps that we can include in our processing before stacking and after stacking. So I'll talk about the stacking. That will lay a foundation for our further discussion. And as I mentioned, stacking is summing appropriate traces in an attempt to enhance the signal and to reduce at least the random noise. So I talked about the seismic method in a couple of the earlier lectures. The seismic method is plagued with noise, both random noise and coherent or systematic noise. One way we can reduce the random noise is to get repeated measurements for a particular point in the subsurface. So as an example, I have a red box here, and what I can do is I can look for a shot that goes down, reflects off of this piece of the subsurface. I will talk about a bounce point, kind of a crude way of referring to it, and it's recorded by this listening device. This shot will hit the red box and be detected by this listening device, and this shot into this, and this shot into this receiver. So we can get in this case, 4 different independent measures of the reflectivity at the red box. Now, if we have noise and the noise is totally random, if we add all 4 of these together, the geological signal will be enhanced, and random noise, because sometimes we have positive values, sometimes we have negative values, the noise will tend to go towards 0. So stacking is a way in which we can enhance the signal and decrease at least random noise. This is an example. If you saw the presentation on Tuesday, I had an animation with a seismic source. Here's the source array, receiver 1, 2, 3, 4, 5, and we're getting reflections. I'm just showing the ray paths for the interface at the level 3 between the white layer and the gray layer. If we look at the shot record, energy that goes straight through the water column horizontally and reaches the receivers is the red events that are shown. This is two-way travel time, and this is offset or distance or receiver number. And the reflections will give us a hyperbolic shaped event when we look at a shot record. And that's because as the energy goes down, bounces and comes up into receiver 1, that's a shorter path, requires less time than the shot that goes off, hits this bounce point, and comes up to receiver 5. And again, we know the physics here, we have the equations, and so this turns out to be a hyperbolic equation that is very well defined. So what we do in processing is we gather or we collect shot receiver combinations that gives us a bounce point, a reflection point at a particular location. And that would be true for any data associated with a vertical line drawn at this location. So now we have a CMP, a common midpoint gather. Gather was a collection, so it's a collection of these 5 shots into these 5 receivers. I think there's probably 10 that are shown here, and the reflections again will be hyperbolic, but the traces may not be evenly spaced given the geometry of the survey and any problems that we may have had getting perfect coverage. So the CMP gather the common midpoint. We can see the different reflections as hyperbola. We can measure the curvature of that hyperbola, and that will give me the average velocity at that location down at this two-way time or this depth. We can estimate what that velocity is, and with that estimate, we can then apply a correction to correct for the delay, very little delay when the offset behind the shot is minimal, very significant delay when the shot and the receiver are separated by 4, 5, or 6 kilometers. So we can calculate what that delay is and try to adjust these hyperbolic reflections so that they'll occur at the time that they would have come in if there was no offset between the shot and the receiver. So we're trying to get things back to a 0 incident reflection. If we use the perfect velocity, then all those traces from close to the source to far away, or from near 0 incident angle to far incident angle, all of those will be flat. And so we talk about flattening the gather. If our velocity is not correct, and let's say the velocity is a little too slow compared to what it is in the Earth, then we won't correct that hyperbola enough, and we will see a little bit of a downward bow to the reflectors. And alternatively, if the velocity is a little too fast, we overcorrect it, And instead of flattening the gathers, the reflectors will curve up a little bit. And so the way in which we flatten these data are now all automated. We have some QC that a human operator will do, but the computer will test different velocities and see how flat or non-flat the different hyperbolic reflections are. And it will indicate which velocity gives us close to being a flat hyperbolic reflection. So we have our common midpoint gather. I have 10 different traces here. We'll do a velocity analysis. We'll come up with the average velocity to the reflector. We'll take out the delay because the ray paths are longer as the distance between shot and receiver increases. That's called a normal move-out correction. And then we'll sum all of these traces and come up with a single composite trace. And if we have 10 traces that are being summed or added, we say that it is 10-fold data. The reason we do this is because there's going to be random noise on each of these 10 traces, and by summing it, a lot of that random noise, almost all of it, should be canceled out. So we stack several traces in order to get rid of that random noise. We're enhancing the geological signal and removing the random noise. And stacking is one of the best methods that we have to improve the signal to noise ratio. So here we have a common midpoint gather. We can see the hyperbola of the reflections. They're steeper here where the velocity is slower. They are less steep here where the velocities are generally higher. The diagram at the top, we're showing shots into different receivers. And so 0 would be 0 offset or 0 incident angle. And this direction along the top, as we move to the right, that incident angle is increasing. The distance between the shot and the receiver is increasing. And so we can calculate what sort of velocity we need to flatten the data. And so this is NMO corrected, normal move out corrected. That's where we estimate what the delays are, try to take them out, and try to flatten the gather. We'll put a mute on to take away some of the artifacts out here. You can see that the reflectors are getting thicker and they start to curve up. And so we'll remove that through a mute. And then we'll sum all of the traces, and that will give us a stacked trace at one XY location. And we do that location after location after location and build up either a 2D seismic line or a 3D seismic volume. So if we stack every available source receiver combination, we call that a full stack. The summation or the stacking reduces the random noise, enhances the signal. This full stack is our best data set for doing structural interpretation, mapping faults. It's also the cleanest data set to interpret because it has the lowest signal to noise ratio. As the fold of the data goes up, the cancellation of the random noise is improved. Summation or stacking of all angles from a near offset to a far offset, or a near 0 incident angle to maybe an incident angle of 30 or 35 degrees, that's going to decrease the overall bandwidth of the data. So a full stack may not be the best data set for stratigraphic detail because of this reduction in the bandwidth. And the bandwidth is the range of frequencies that's within the data set. And it also may not be the best data set if we're investigating certain types of direct hydrocarbon indicators, DHIs. We can generate, instead of a full stack, a partial stack. And the diagram here, we have our source boat, or our acquisition boat with our source, and we have receivers. If we look at the furthest receiver, at this depth, that incident angle, which is equal to the reflected angle, is 25 degrees. But as we go deeper, that angle gets smaller. So the maximum angle here is 20. If we went even deeper, it might be 15 or 10 degrees. So the angle of incident for each shot into each receiver is going to vary, and the maximum is dependent on the depth. What we can do is we can break our gathers into those that are associated with small angles or near shot receiver pairs, mid-range, and also far range. And I'll talk about why we might do that. Here we have an example where we have a shot, a bounce point, and a receiver for a deeper level and a third level. And so the angle of incident is changing as a function of depth. What we can do is we can plot two-way travel time and distance between the shot and the receiver, or offset, or trace number, and we can calculate where the different angles of incident angles of reflection lie. So the first black line is 5 degrees, 10 degrees, 15, 20, 25, 30, and so on and so on and so on. We can then compute a mute so that if we just stack the data between the two red lines, on average, it's from about 8 degrees out to about 20 degrees. And we could call that a near angle stack. From the first red to the first, or I'm sorry, the second red to the first green, that's the angles of about 25 to 35. That could be our mid volume. And then we could stack only data that has an incident angle of 35 to 45, and that would be the far. We can see that in order to get good data with depth, sometimes we have to adjust those mutes so that we're not quite at those angles, but we are at the smaller angles, the mid-ranges of angles, and the larger amounts of angle. So here's an NMO, normal move out, corrected CMP gather, so the hyperbola have been flattened. We can calculate what the mute is for 5 to 15 degrees and what it is from 25 to 35, and just stack those data. So the near angle stack would be between the two red lines, so it would be these data would be summed. And we can also do a far angle stack where these data are then summed. So whenever we talk about a partial stack, we will not have as much fold, we will not have as many repeat measurements as we do in the full stack, but there are some important changes between what a response of a particular reservoir might be in near stack amplitude versus far stack amplitude. And I'll be talking about that as these series of lectures proceed. If you have heard of AVO, or amplitude versus offset, that is this geophysical anomaly that we sometimes detect when we have hydrocarbons in reservoir rocks. There are a number of steps that we can do before stacking. What we want to do is correct amplitude loss with depth or two-way travel time. We may have to correct for elevation changes if we're dealing with a land survey where all the shots and all the receivers are not at or close to sea level. We want to minimize the effect of the seismic wavelet, and that's a process called deconvolution. And we want to determine the optimum velocity function for stacking the data. So these are 4 examples of some pre-stack processing steps. First, that we can consider is the amplitude loss as a function of two-way time or distance. So if I have an explosion where the red symbol is shown, with time, that energy will spread out spherically, and energy along the red band versus the yellow band versus the purple band will become more and more dilute as the area over which the energy is spread increases. That energy variation decreases as 1 over the radius squared or 1 over the two-way time squared. And so we understand this phenomena of spherical divergence. We know it's related to the radius squared. And so understanding that, we can then compensate for the loss of amplitude due to spherical divergence. We can also have some transmission loss. And so as the energy goes down and is reflected off of n number of reflectors, let's say 1% of the energy reflects up and 99% goes down, and 1% reflects up, and so 98 roughly percent goes down, and so on and so on and so on. We can calculate how much transmission loss would there be so that we can normalize the energy at each interface that hits it, trying to get close to the energy that hit the first interface. We also have amplitude loss due to absorption, and that is because the seismic energy gets converted into heat, and absorption is a frequency-dependent effect. The higher the frequency, the greater the loss of signal. For the processing people, they talk about a Q factor, and that's related to this absorption phenomena. And Q, or absorption, varies by the rock type. And so amplitude A0 would be the initial amplitude, and then we have an exponent, and here's the Q term. As an example of that, if we're at a low frequency, say 5 hertz, this shows how the amplitudes are attenuated as the path length increases. If we're at a higher frequency, say 50, this is the attenuation. So as a point of reference, I've marked where it's 1,000 meters of path. So the high frequency, after 1,000 meters, we've lost 80%, we're down to 20%. But at 5 hertz frequency, we've only lost 17%. Our amplitudes remain 83% of the original. So this is a reason why on seismic data, usually you see higher frequency content, skinnier peaks and troughs in the shallow part of the section. And as you get down to 1 or 2 or 3 or 4 seconds of two-way travel time, the reflectors seem to fatten up. And that's because we lose the high frequency data. One correction that is commonly used, it was universally used when I started back in the late 70s, is gain compensation. The simplest and most destructive in terms of preserving the true amplitude relation to reflection coefficients is called automatic gain control, or AGC. And so the diagram here, this is the original data. And what they do is they do a 15 sample running average. And if the average is low, they increase the gain. And if the average is high, then they don't increase the gain quite so much. So this is the gain function that was applied. And so we boosted the gain because we have a region with relatively low amplitudes. And that sliding 15 sample AGC has destroyed the fact that there's less impedance contrast in this portion of the trace, more impedance contrast here, and an intermediate amount here. What we'd rather use is a program gain control similar to spherical divergence. Here's the input trace again. It's the same one as on the left. We're going to gain the section as a function of depth, but we're going to do it linearly. And so the deeper things have been increased in amplitude relative to the shallow, but we've preserved the overall sense that we have a low amplitude zone in the center. If we're dealing with land data, then we may have to make a correction for elevation changes. As we look at shot receiver pairs, the elevation for the shot is going to vary if we have topography in our land survey area, and the elevation of the receiver can also change. And so if we don't correct for that and the shot and the receivers vary in elevation, it will distort our hyperbolas. So we won't see nice hyperbolic reflections. What we will do is we'll define a seismic reference datum. We'll apply corrections so that it will be as if the shot was on that datum plane and all of the receivers were also on that datum plane. What we need to know is the correct elevations, and we need to have an estimate of what the near surface velocity is. If we apply those corrections, then we start to see our hyperbola once again. Here is an example, a land survey. This is before static corrections were made. And so you can see hyperbolas, but they're not all that clean. They've been distorted because of elevation variations. After we do the static corrections, the hyperbolas are much cleaner, less oscillating, less ratty, and will give us much higher seismic data quality. What we typically do is apply a mute to take out areas where we have direct arrivals or refracted energy. And so we'll concentrate on the reflections, the hyperbola. So this is before the mute. This is the after the mute. Then we would do a normal move out correction to flatten the hyperbola. And then we would stack to get information for a particular location XY. The other thing we want to do is remove as much as we can the distortions in the geological signal due to the shape of the wavelet. Our wavelets do not have a zero time duration. Usually it's on the order of 20 to 40 milliseconds. So deconvolution is a series of processes that the data processors apply to try to correct for the fact that we have a wavelet shape. Again, one picture is worth 1,000 words, or I guess I have two pictures of before the decon was applied and after. And there's some ringing here and down here, and the ringing has been removed. We're getting much nicer, cleaner hyperbola. And so when we flatten and stack, we're going to get much improved data quality. We also can have multiples in our data set. Multiple is where seismic energy has been reflected more than once. Another way to say it is that there is more than one downgoing path and one upgoing path. So here we have a water bottom multiple as one path down, one path up. It hits the air-sea interface, reflects back down, second path down, second path up. And so that's a water bottom multiple. We can also have subsurface multiples and things that are called peg leg multiples. If we can understand how these multiples are generated and where they might occur and isolate them from the primary data where we have a single path down and a single path up, we may be able to remove the multiples and improve our image. We do our velocity analysis. Here's a common midpoint stack. So this is before it's been flattened, and then we're showing 3 hyperbola. The software will go in and use different velocities here from 5,000 to about 10,000, and we'll see how flattened each of these hyperbola are. and the data that's displayed here as contours is a value that indicates how flat the reflectors are given a particular velocity. So up shallow, a velocity of about 6,000 seems correct, but down here, a velocity of about 7,000 or 8,000 would be better. This is a semblance diagram. This is where we're showing two-way travel time and the velocity that was used to stack the data. Oops, I'm sorry. And the colors here is the number that indicates how flat the gathers are. The hotter colors are flatter gathers. And here, this is the true velocity for the shallow section. And then it's a little hard on this display to see why the velocity interpreter picked it out here. But this is repeated here, and it's repeated here. This is multiple energy. And so in a velocity semblance diagram, the multiples tend to lie in different space. And so we can design filters to filter out this part of the data. So here we have a gather. Here's a mute's been applied. It's been flattened. And here we have something that's still hyperbolic. That is multiple energy. And so when we stack the data, summing all of these traces, and maybe there's 40 traces there, because this is dipping, when we sum it all or do the stack, that multiple energy will cancel out quite nicely. Again, this is a normal Moveout corrected gather. We have flattened a lot of the primary reflectors. We still see some events that are curved down. That would be due to a multiple. If we stacked just near trace data, the multiple still curves down, but not that much. If we summed all of these traces, we would not necessarily cancel all of that multiple. However, if we do a far angle stack, we have more inclination on the dipping multiple energy, and that would be more effectively removed. So when we talk about a partial stack, we may still have a lot of multiples in the near stack section. We would not have as many multiples in the far stack section. And if we do a full stack and we take all of this energy, then this yellow event would get canceled out through the summation. So our multiple removal, if we're talking about marine data, the technique that we use is determined by how deep the water is in our area. If we're in a deep water area, we'll use velocity separation, which is also called a radon filter, and that's what I was describing. Here's primary. This is multiple. This is multiple. So what we'll do is design filters that will get rid of these multiple energy effects. If we're in a shallower water environment, we may not be able to use a radon filter, and then we'll rely on deconvolution processes to try to eliminate or minimize the effect of multiples. In land, we tend to use the radon or decon. Again, it depends somewhat on the area and how well radon filtering will allow us to identify and remove multiple energy. Here is a set of pictures again. On the left is some seismic 2D profile before the multiples have been removed. The multiples are going to be removed using a radon filter, and this is after. And you can see, for example, in this portion, we have angles or events that are coming down at a steep angle and other events that are a little bit more horizontal. When we remove the multiples, it turns out that these slightly dipping to the right events are multiples associated with something much shallower, and the radon filter has eliminated a lot of that multiple energy. We can do pre-stack processing. There certainly are advantages of doing some of the processing pre-stack, but these pre-stack processes is a little bit beyond the scope of a 30 or 40-minute lecture. They are quite expensive in terms of money, in terms of time to get the processing done, and resources that would be the people involved and also the hardware, the computers that we would need. So let's move on to seismic migration. Most of my diagrams thus far, I've had nearly horizontal interfaces, but if we have dip on the interface, the angle of incidence equals the angle of reflection. We draw a perpendicular to the interface, and that's where we measure these angles. So if I have dip on the interface, I may have a shot here. The energy would go down, bounce off of this point, and be detected here. And so the bounce point is not at the midpoint as it was if the interface was flat. So we have to have a way in which to correct if we do not have flat-lying interfaces. And it's more common to have interfaces in our area of study that are not flat than to have things that are flat. So this is taken from the first exercise for Unit 15. We have an interface that's dipping here. We have a source, and we'll assume the receiver is at the same location. The energy travels down. It hits this interface at 90 degrees. It bounces, and it comes back up. If it takes 0.2 seconds to go down, it also takes 0.2 seconds to go up, or a total of 0.4 seconds. When that information gets plotted on a seismic section, it will be plotted underneath the midpoint, or if it's a zero offset shot and receiver at the same location, it'll be plotted right underneath the shot receiver pair at position B. And so the interface is at A, but the seismic reflection is at B. And so we have a mispositioning of the reflector. And so our seismic trace at the shot receiver midpoint would be at the right travel time, but it would be in the wrong position. So if I considered 6 shots into 6 receivers, all zero offset, I can use a compass and I can plot where each of the reflections would be posted on a 2D seismic line. And so the first exercise would have you do that. If you do that, you would find this would be the reflection for position 1, 2, 3, 4, 5, 6. So the interface is the black line, but the reflection is the red line. And so the reflection is always positioned down dip, so it's shifted to the left here, and it always has less dip than the actual interface in the subsurface. So we have some imaging problems. We can do a correction if we understand the physics, which we do here. And so what we want to do is reposition reflectors associated with dipping interfaces so that this mispositioning problem is solved. And we do that through processes called seismic migration. So let's consider we have a trace with a single peak trough. We know what the 2A travel time is, but we're not sure where the position is. If it was flat, it would be down here, but in theory, it could be any place along the dotted blue arc. We can take several reflectors. We can swing these hypothetical arcs, and where they constructively interfere would be where the interface actually is positioned. I should mention that the radius of these circles is related to the average velocity to the depth where that reflection occurs or where the interface occurs. So this is, we're using 3 traces. If I use 11 traces, again, I'm interested in where that peak starts. I can swing out arcs based on the average velocity, and where I have the constructive interference, that is where the interface actually lies. And so the raw seismic, before we do seismic migration, the reflector would be at the red position. The subsurface interface is at the blue position. And so seismic migration is a process by which we calculate what that mispositioning error is, take it into account, and we migrate the seismic reflections back to where the subsurface locations associated with them actually occur. So here is a model of some seismic data. This is the unmigrated seismic data. We apply migration, and now our peaks have been moved. Our peaks have been moved, and in each case, from the unmigrated data in red to where they actually occur, we have to move up dip, and we have to have a steeper angle. The migration process itself is not perfect. We do get migration noise, low amplitude events that we will have to try to correct for as we process the data. Here is an example. This, I believe, is from the Rocky Mountain area, might be in Wyoming. This is the data before we do the seismic migration, and so the reflectors, the blacks and the whites, are not in the correct position, and our imaging is not so great. You can see in this area we have some dipping reflectors and some flatter reflectors. Whenever we see cross-cutting dips, that's a suggestion that we have some misposition problems. And this is what the data look like after a fairly simple post-stack migration has been applied. And now you can actually see where a thrust fault is positioned. And so the next slide will compare, this is before migration or unmigrated, and this is after migration. And we have a much better representation of the subsurface geometries with the image after migration than we had before. So migration, there's a number of different algorithms that are available. There's advantages and disadvantages for each. Some are simple and quick, and they're not as accurate. And with seismic migration, the adage, you get what you pay for, or you get what you're willing to pay for, is correct. So post-stack time is the fastest and cheapest. It can give us fairly good imaging. Pre-stack time migration is a bit more expensive. That's going to improve the imaging quite a lot. And our best imaging comes from pre-stack depth migration, which is several orders of magnitude more expensive, takes 2 or 3 or 4 times as long to generate, but it will give us excellent imaging. So which type of migration should we use? What we consider is 2 factors: geological complexity from very simple layer cake geology to highly structured geology. And then we look at how the velocities vary horizontally. Is it very smooth or is it highly variable? And so if the geology is not very complex and the velocities are only varying very smoothly, post-stack time migration is probably the proper way to go. If the geological complexity gets a bit more intense and the lateral velocity variations become more significant, then we would do pre-stack time migration. If the geological complexity increases some more and the lateral variations increase some more, we would do pre-stack depth migration. And if we're in a very highly structured area with very high variability in velocities, then we would use pre-stack depth migration, either with a beam migration, a wave equation migration, or a reverse time migration. And we're talking about relatively inexpensive to extremely expensive turnaround time of maybe a month to maybe a year or 2 years to get pre-stack depth migration. So one of the things we worry about is how quickly do the velocities vary laterally, and this is the spread length. So this would be the distance from the nearest receiver to the furthest receiver. So that might be 2 kilometers or 5 kilometers or 8 kilometers. This pattern in here is meant to represent salt. And so salt is got a very significantly different higher velocity than sediments. And so if we're in this area, the lateral velocity changes are small. If we're in here, they're very high. If we're over here, they're somewhat moderate. So depending on the geological complexity and the variability in the velocities, that would dictate what type of seismic migration ideally we would like to have. I'm running a bit out of time, so I think I'll just skip these guys and leave a few minutes for questions. I'll show this, which is our syllabus, in case we need to talk about either former lessons or lessons that are on deck. So I'll turn it over to Dr. Sumi for a few questions.
Well, thank you, Fred. The first came in from Solito, and he just asks, what is seismic phase?
Seismic phase, if you've been with me for some of the other lectures, I've talked about zero phase data and minimum phase data. And those are kind of end members. The phase is the basic shape of the wavelet given one single reflection coefficient. Zero phase, the wavelet will be symmetric and most of the energy will be associated with where the change in impedance actually occurs. If you're talking about minimum phase, that is an asymmetric, it's either a peak followed by a trough or a trough followed by a peak, and the waveform starts at the position of the reflection coefficient. It's not centered on the reflection coefficient. And I think I talked about that in lecture 6.
Great. That was the only question we've had so far. So given that it's 2:55, I'm going to go ahead and wrap this up. And thank you so much, Fred, for that great lecture. It was awesome. And yeah, we'll see you next Tuesday for 3D seismic data. All right, take care, everyone.
Okay, thanks to everyone for tuning in.
All right, bye.
Goodbye for now.